In this section, we will revisit the sampling distribution, but this time we will explore the central limit theorem for proportions. So we will treat the sample proportion as a random variable, whereas in the previous section we treated the sample mean as the random variable. So let's dive in. We will go over how to construct the sampling distribution for a sample proportion, and then we will use the central limit theorem to compute probabilities for sample proportions. So to get started, let's just kind of go over some terminology and some notation here. In a population, the proportion who have a certain characteristic is called the population proportion. And in statistics, we typically use the letter p, lowercase p, to denote the population proportion. Now let's say that we collect a simple random sample of n individuals from a population, and we let x be the number in the sample who have a specific characteristic. Then the sample proportion is found by taking the value of x and dividing it by the sample size, n. And the symbol that we typically use to represent the sample proportion is p with that little hat symbol on top. Sometimes we just call that p hat. So, for example, let's say that a computer retailer wants to estimate the proportion of people in her city who own laptop computers. She cannot survey everyone in the city, so she draws a sample of 100 people and surveys them. Then it turns out that 35 out of the 100 people in the sample own laptops. So then the sample proportion is found by taking the 35 people in the sample who own laptops, and dividing that by 100, right, the number of people in the sample. That would be distinct from the population proportion. The population proportion would be the proportion of people in the entire city who own laptops. And that would be the value of p. So, let's say we have a large population, and in this diagram, the rectangle there represents the population. From a large population, as we mentioned in the previous section, you could collect a simple random sample from that population, but because the sample size is quite small compared to the population, you could collect several different samples. In fact, you should be able to collect a lot of samples from within one large population. The samples will not all be the same, right? They'll be composed of different individuals. And for each sample, we could compute a sample proportion. And because each sample proportion is based off of a different sample, then the sample proportions will differ from each other. And so we can treat the sample proportion as a random variable, which means it has a probability distribution. And the probability distribution of the sample proportion is called the sampling distribution of the sample proportion. So to explore this concept, let's work through an example. Let's say that we toss a fair coin 5 times. If we do this, this will produce a sample of size 5, where each item in the sample is either a head or a tail. So the sample proportion, in this case, will be the proportion of times that the coin lands on heads. Now, the population proportion, we can just treat that as 0.5 because that is the probability that it lands heads each time. And according to the law of large numbers, if we were to toss the coin numerous times, the proportion of heads would be about 0.5. So 0.5 is the number that we will treat as the population proportion. Okay? But if we toss the coin 5 times, then there's a total of 32 possible combinations of heads and tails that you could obtain. And we'll treat these as 32 independent samples. Okay? So here's a comprehensive list of all the 32 possibilities. Right? So like, for example, it's possible that all 5 tosses are tails. Or you might have something where the first 4 tosses are tails, the last one is a head. Or you might have 3 tails and then a head and then a tail. Or you might have 3 tails and 2 heads and so on and so forth, right? So there's 32 possibilities here. And each sample has a sample proportion that goes with it, and that proportion is the proportion of heads in that particular sample. Okay? So like this sample has a sample proportion of 0 because there are 0 heads, right? This sample has a sample proportion of 0.2 because there's 1 head out of 5 coin tosses. So 1 divided by 5 is 0.2. This sample has a sample proportion of 0.4 because there's 2 heads out of 5 coin tosses. 2 divided by 5 is 0.4, and so on, right? So we've got 32 samples and 32 sample proportions. Now, what happens if we compute the mean of this random variable? The mean would be found by taking all 32 sample proportions, adding them up, and dividing by 32. And if we did that, we would get 0.5, and we call this the mean of the sampling distribution, and the symbol we use for that is this mu with a subscript with the p hat there. And then the standard deviation of the sampling distribution would be found by computing the population standard deviation of all 32 sample proportions. If we did that, the number we would get is 0.2236. Okay? Now it turns out that the mean of the sampling distribution and the standard deviation of the sampling distribution are related to the population proportion and the sample size in the following ways. First of all, we said that the population proportion of heads is 0.5, right? And that is equal to the mean of the sampling distribution, which is also 0.5. This is a relationship that always holds, okay? The mean of the sampling distribution of p hat is denoted by this mu with a subscript p hat, and it equals the population proportion. Now, the standard deviation of the sampling distribution is 0.2236, and this is also related to the population proportion and the sample size. It's not obvious just by looking at that number what that relationship is, but it's governed by this formula here. It's actually the square root of p times 1 minus p divided by n. So p is the population proportion, which is 0.5. N is the sample size, which is 5. If you plug those numbers into this formula and compute it, you would get the standard deviation of the sampling distribution. Okay? So the standard deviation of the sampling distribution of p hat, the symbol we use for that is sigma with the subscript p hat, and the formula that relates it to the population proportion and the sample size is this. It's the square root of p times 1 minus p over n. Okay, so now let's take a look at a couple of histograms. Okay. So if we take the, if we were to develop a probability distribution, the distribution would, let's see here, let's back up a little bit here. If we come over here, just pause here for just a minute, okay. Get my pen here, and color, I want black. So a probability distribution would look something like this. We'd have a list of the random variables. Now we're going to call this list p hat because the random variable in this case is the sample proportions. And then over here we'd have the probabilities of each of those values actually occurring. Okay. So the possible p hat values are 0. If you look at the list, you see that some of them are 0.2, some of them are 0.4, some of them are 0.6, some of them are 0.8, and then we see one of them is 1. Okay, and the probabilities would be, you would fill in, right, by computing, assuming equally likely outcomes. So, for example, the probability that the sample proportion is 0, we would come up here and say only one of these sample proportions is 0. And there are 32 total, right? So that would be 1 divided by 32, which is equal to 0.03125. So that's what you would put right here, 0.3125, okay? 0.2, we would count the number of 0.2s. I see 1, 2, 3, 4, 5. I see 5 0.2s, right? So that would be 5 divided by 32, which is 0.15625. 5.625. 0.4, if we count those, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's like 10 of those. So 10 divided by 32 is equal to 0.3125. 0.3125. 0.6, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those as well. So that's also going to be 0.3125. 0.8, looks like we've got 1, 2, 3, 4, 5. So that's going to be same as 0.2, 0.15625. For 1, the only one is down here, right? 1 divided by 32 will be the same as 0. So well, anyways, 0.3125. So anyways, handwriting is a little sloppy there, but you get the idea, right? So so then the histogram, right, just in the base, the way we've always done it, you would have these 5 values along the horizontal axis, and then the height of each rectangle would be dictated by the probabilities. Okay, so moving ahead, this is the resulting histogram right here from that probability distribution that we just put together there. Okay, and what you can see is that the distribution is reasonably well approximated by a normal curve. Let's say that we do the exact same experiment again, but this time with 50 tosses instead of 5. Right? Everything else remains the same. Well, if you're doing 50 tosses, there's going to be a lot more than 32 possible combinations of heads, tails, right? And so your probability distribution will be a much longer distribution. Your histogram will have a lot more rectangles. This is what the histogram would look like right here. Okay, and that one's even more. That one can be is even a better approximation of a normal distribution than with 5 tosses, right? So basically, what we can see, the trend here is that as we increase the number of coin tosses, the sampling distribution of p hat looks more and more like a normal curve. Okay. Now, in our case, we have a sampling distribution that is somewhat close to normal, even for a small sample size, right? Even with sample sizes of size 5, our sampling distribution, even in that case, looks pretty close to normal. Up here, you can see that, right? And that's pretty much always going to be the case when your population proportion is close or equal to 0.5. When the population proportion is closer to 0 or closer to 1, in those cases, you will need a larger sample size in order for the sampling distribution to be close to normal. A common rule of thumb that's followed as far as how big your sample size needs to be. We could say that the distribution may be approximated with a normal curve whenever the product of n times p and n times 1 minus p are both at least 10 or more. And remember that n is the sample size, p is the population proportion. So all of that can be summarized into the central limit theorem for proportions, which says, let p hat be the sample proportion for a sample of size n from a population with a population proportion p. If n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, then we can treat the sample proportion as a random variable, and the distribution of the sample proportion will be approximately normal. The mean will be equal to the population proportion, and the standard deviation will be equal to the square root of p times 1 minus p over n. Okay? So, compare this to what we covered in the previous section. In that section, we treated the sample mean as a random variable, and we came up with a similar theorem, which we also called the central limit theorem, in that case for means. And in that case, the mean of the sampling distribution was equal to the population mean, right? And the standard deviation of the sampling distribution was equal to the population standard deviation over the square root of the sample size. And the sample size requirement in that section was that n should be greater than 30 to guarantee that the distribution is approximately normal, right? So up here is the central limit theorem for proportions. Down here is essentially the central limit theorem for means. Okay? So let's go over an example here. According to a Harris poll, chocolate is the favorite ice cream flavor for 27% of Americans. If a sample of 100 Americans is taken, what is the probability that the sample proportion of those who prefer chocolate is greater than 0.3? Okay? So we will apply the central limit theorem for proportions to solve this problem, because the question being asked is in regards to the sample proportion, right? So we have to treat the sample proportion as a random variable. First of all, we need to check our assumptions to see if we can justify treating the sampling distribution as a normal distribution. So to do that, we take the sample size and multiply it by the population proportion. The population proportion is the 27%, or 0.27, right? It's the population proportion of people who say chocolate is their favorite ice cream flavor. Okay? So n times p would be 100 times 0.27, and that's equal to 27. And that number is definitely greater than 10. N times 1 minus p, that's equal to 100 times 1 minus 0.27. And that's equal to 73. And that number is also greater than 10, right? So the sample size is sufficiently large for us to treat the sampling distribution as a normal distribution. So we can go ahead and sketch a normal curve. And this curve is centered over 0.27 because, according to the central limit theorem, the mean of the sampling distribution is equal to the population proportion, which is equal to 0.27. And we're trying to find the area under this curve to the right of 0.3. Okay? Because the question being asked is, what is the probability that the sample proportion of those who prefer chocolate is greater than 0.3? So we shade the area under the curve that we want to find right there. Okay? And to find that area, we need to either calculate the z-score and then use the chart, or we can use our calculator in the normal CDF command. Now, if we were to use the chart, we would have to calculate the z-score. And remember that the basic z-score formula, when we first introduced it, was z equals x minus mu over sigma, right? Now, the basic format of this is you take the random variable, you subtract the mean, divide by the standard deviation. But in this case, the random variable is actually the sample proportion, and the mean is actually the population proportion, and the standard deviation is governed by this formula. So I'd like to go ahead and use a modified version of this formula and write it like this. Z is equal to p hat minus p divided by the square root of p times 1 minus p over n. Sorry for the lack of space there, right? So if we make that calculation, p hat is 0.3, p is 0.27. Standard deviation is calculated for us down here, so it's 0.044396, and that works out to be 0.68. Okay. Once you have the z-score, then you can go to your chart, and if you find the number in the chart corresponding to the z-score 0.68. And then remember that you have to take 1 minus the area you find on the chart, because we want the area to the right, not the area to the left. Okay. If you were to find the area using the TI-84 calculator, you could use the normal CDF command. You would put 0.3 in for the lower endpoint, 1E99 for the upper endpoint, 0.27 for the mean, and then the 0.044396 for the standard deviation, and run that. So that would be the alternate way of finding that area. Either way, whether you use the table or the calculator, you should get a result that says about 0.2496. That is what this area is. And so that's also the answer to the question. We could say the probability that the sample proportion of those who prefer chocolate is greater than 0.3 is 0.2496. Okay. All right, one more example. Approximately 60% of eligible voters voted in the 2016 U.S. presidential election. If a sample of 88 eligible voters were polled, would it be unusual if less than half of them had voted? Okay. So the population proportion is the 60%, or 0.6, right? And the sample proportion would be based off of the 88 voters. And we would want to say, is the probability of less than half of those 88 randomly selected voters having voted, would that be unusual? So we need to find the probability of that event and then see if that probability is less than 0.05 or not. So we can do that once again using the sampling distribution. But first of all, it's important to, again, verify to see if the sample size is sufficiently large to treat the sampling distribution as a normal distribution. So we do that by taking the sample size, which is 88, and multiplying it by the population proportion, which is 0.6. And that gives us 52.8. That number is definitely greater than 10. Then we take the sample size and multiply it by 1 minus 0.6, and that gives us 35.2, which is also greater than 10. So yes, the sample size is sufficiently large. So we can use the normal curve. Now, so the next step would be to sketch a normal curve, and it occurs to me here that there's actually a mistake in the diagram here. And because the mean of the sampling distribution is equal to the population proportion, which is equal to 0.6, So that means our curve should be centered over 0.6, and this shows it centered over 0.51. So cross that out. That should be a 0.6 right there. And then it says we want to find the probability for that the sample proportion is less than half or less than 0.5. So this shows the area to the left of 0.4. We want the area to the left of 0.5. So I'm going to say, probably something like 0.50. Okay, cross that out. We want to find the area to the left of 0.5. Okay. So if we were to use the z-score and table option, we take z equals 0.5 minus 0.6 and divide that by the standard deviation, which is the square root of p times 1 minus p over n, and that's computed right here. So that would be 0.052223, and that works out to be negative 1.91. So then we'd go to the chart, and we would just find the area to the left of z equals negative 1.91. And that would be our answer, okay? Alternately, you could run the normal CDF command on your calculator. We would use negative 1e99 for the lower endpoint, 0.5 for the upper endpoint, 0.6 for the mean, 0.052223 for the standard deviation. The answer that you get either way should be about 0.028, which is definitely less than 0.05. So we would say yes, it would be unusual for the sample proportion to be less than 0.4. And that wraps it up for this section, right? We've looked at the basic notation for sample and population proportions, how to construct the sampling distribution for a sample proportion, how to find the mean and standard deviation of the sampling distribution of p hat, and how to use the central limit theorem for proportions to compute probabilities for sample proportions. So that's it. Thank you.